In our last class, we have studied about the particle's motion in two-dimensional Cartesian plane when only gravity was acting. Okay, so this was the figure. At any point, you are projecting the particle with some velocity. So it follows this path, and mg is the only external force acting on it. There was no resistance, nothing. Now, for today, we will consider the gravity is acting as it is, along with it, a resistive force is acting. Now, the resistive force, as the name suggests, it will try to resist the motion of the particle, right? So, what was the motion of the particle? We can recall that we have just thrown the particle from this point O. So, it will try to move in this direction. mg is acting, okay? But now there is an extra force which will try to resist the motion of the particle. So, the direction of the force will be opposite to the direction of the motion. Now, any force works tangential to the path of the particle trajectory. Okay. So this is the force, and the direction of the force is not this one, but this one, F. Because your particle is moving in this direction. If the force was helping in your motion, then this would have been the direction. But the force is resisting your motion, so it should be in the opposite direction. Now let us draw it separately. And before that, you can just consider this one. If I consider this as a tangential direction as a whole, this is a psi. Now automatically this is also the psi. So let me just resolve the forces. Thus, this is F, right? So it has two components. If it is psi here, then this is F cos psi, and this is F sin psi. So you can easily now fit this one in the figure here, so that you can see this F cos psi is acting in this direction, that is negative x-axis direction, and F sin psi is acting in vertically downward direction, that is negative y-axis direction. So along not along this x-axis, what are the forces which are acting? Minus F cos psi, right? And along y-axis, what are the forces acting? Two forces, minus mg and plus of minus F sin psi. Minus I is justified, as I already said, because they are working vertically downward, whereas your y is increasing along the vertically upward direction. Okay. So from here, you can easily frame the equations of motion, right? So that what are the equations of motion? Say am d2x dt2. Please, if you recall back, then you will just see that earlier, when only gravity was acting, there was no acceleration along the horizontal direction. But here now acceleration is there. So minus F cos psi. Okay. And along the vertical direction, earlier it was only minus mg. Now it's minus mg plus of minus F sin psi. Okay. Now, what is the psi? As I said again, it is just the inclination of this tangential vector along which your resistive force is acting. Now let us see this one separately, because I need to do what? I need to replace this cos psi, this sin psi in terms of the curves coordinates, that is dx, dy, and ds, where ds is the arc length. So suppose this is your curve, what does it represent? It is a motion direction of, or the path which is followed by the particle. Suppose at any time t, the particle was here, force is acting, and so the particle has been displaced, or has moved rather, from here to this point, neighboring point Q. So this, or let me just draw it properly. This one is the chord joining P and Q. So you can say if I have started from here, and say from O I have started, for O to P, if it is your S, then from O to Q, that is, let me write OP is your S, then OQ is what? S plus del S. Okay, so what is the small amount of change in the arc length? So when it is taking place? In time del T. Okay, so now you see, for this is very small, we can understand, because we are saying that I am moving from P to a neighboring point, not a far away point, but a neighboring point. Why? Because we have to apply the limiting condition, limiting approach, because we have to apply ultimately del P tends to 0. That is instantaneous thing we are trying to observe or rather study. Okay. So for that thing, you can see from here, okay, suppose this is your arc length del S. If it is very small, then this del S, that is PQ arc length will be approximately equal to the length of the chord PQ. Okay, and you can see if easily from here, if your del S, that is S is changing by a del S amount, you are here, so P is a point, say xy, and Q is a point, say x plus del x, y plus del y. Then, what is the change in the Cartesian ordinate and the abscissa? Del x, del y. So actually, I can write here del x, del y. And what is this angle? This angle is the psi angle. Okay. Now you see, this is the chord, but when del t tends to 0, you can easily understand if del t is tending to 0, what are the things that are happening? If del t tends to 0, your arc length is decreasing. So this chord, initially, it was like this, then this, then this. So ultimately, you are going to get a tangent at this point. So as del t tends to 0, we are getting a tangent at P. Which one? The chord PQ tends to the tangent at P. That means the inclination of this and tangent to the with the horizon, we are considering the horizon on the horizontal plane rather, or the x-axis direction, is we can consider the angle of inclination of the chord PQ in a limiting condition. So I can say here it is psi, because initially I said psi is the angle that the tangent makes with the x-axis. Okay. So now if I consider this figure, you can easily see the cos psi inverse. It is dx cos psi. Okay. Then dx ds, and sin psi, it is dy ds. Instead of del x del s, del y del s, I am writing dx ds because I have already applied the limiting approach. That's why this tangent and the chord are approximately the same in the limiting condition. Okay, that's why I can get this cos psi and sin psi as I said here. So ultimately, if I have applied on the left hand side, I have applied the del t tends to 0, then on the right hand side also I have to apply that. That's why I'm getting the from del x del s to dx ds. That is differentiation of x with respect to s, and here also differentiation of y with respect to s. So ultimately, my main thing, that is the main motive of in our to input in our calculation was this one. Yeah, I have to, as I said, I have to replace this cos psi sin psi in terms of dx, dy, and ds. Okay. So now you can easily understand that I can plug in these expressions of cos psi and sin psi in my equations of motion. And this will simplify our calculations so that we can progress further and find out the trajectory again when you are moving the particle, or rather projecting the particle with some velocity in a plane, in a particle plane. That means gravity is already there, and also with it there's a resistive force. Okay, so this is the fundamental idea. Now let us see what are the calculations they have done so as to get the trajectory. Okay. So as I said, these are the equations of motion. You have projected the particle from here again with some initial velocity u, nothing extra here coming. What is extra coming? This mkb, this force F I have said, right? Here they are giving a particular, or rather a specific expression of the force. This is the magnitude of the force. Okay. What it is saying? Resist the motion. You just read the statement. A particle is projected with velocity u at an inclination alpha, acute above the acute angle, obviously we are considering, above the horizon in a medium that resists the motion by a force k into v per unit mass. Okay, where v is the velocity of the particle at any time t. So we need to prove that this will be the equation of the trajectory. Okay, acha. So we have considered as usual the scenario. This is the point of projection with the velocity u. And these are the equation of motion because we have now considered the resistive motion. And as they have demanded, k into v is the velocity, the magnitude of the force. So I have taken this per unit mass. So if having the mass of my particle, then mkb is the total force magnitude. So mkb. And see, as I said, the direction is like this because v is the velocity of the particle, which is directed in this because your particle is moving in this direction like this, as I said earlier in the figure. Okay, it's moving along this path like this. Okay. So as I can simply put it here, now you see this d2 is to get the first equation of motion with or with respect to x-axis. If you see what they are doing nothing extra. They are replacing v by ds dt. Quite obviously, because if it v is the velocity, then v is ds dt. That is change of rate of change of the arc length with respect to time, right? So ds dt. And where from this dx ds pops in, it is the Cauchy expression replaced by dx ds as I have shown earlier. So ultimately you are going minus k dx dt. And simply from here you can simplify it and integrate it once so as to get this one. This is easy, just straightforward. And now use initial condition again. So dx dt was what? Use component along x-axis. If you have projected the particles here along with alpha angle, okay, then u cos alpha is your project or component of the velocity, initial velocity. So u cos alpha equals to dx dt when t equals to 0. So that's what I am putting. So u get fixed and ultimately you are getting this simplified expression. Again, you can integrate it. So you are getting this thing. And as we already know, we are trying to find out the trajectory. So ultimately we need x, y in terms of uh, t. Okay. So I am just moving along for that motive. X, earlier there was x double dot. From there I have integrated once to get x dot. Then once again I am integrating to get x. Now you see x, some function of t is coming. Again you are using initial condition as usual. So b also gets replaced via this, and ultimately you are getting x equals to this expression. Okay. So this x in terms of t has already come. Now is the same thing we need to do for y. And for y, what were the things? You will just see from here, you can easily see. My m will be cancelled out because m is non-zero quantity. Minus g minus kv sin psi. So v is again we are going to get this expression for v from here. So ds dt and dy ds for the sin psi part. Again, you can just simplify it or rather group together the terms so that you get like this. Okay. Okay. Then you integrate it once to get y dot. Again, use initial condition with u sin alpha as the now the vertical component of the projection velocity. So your c is getting fixed. So you can put all this together and ultimately you get y dot in terms of like this. Again, you can integrate it again once again to get y in terms of again use the initial condition to replace d by some specific constant, and so ultimately you are getting this. So I have obtained x and y both as functions of t. Now what remains to do? That remains to just you replace somehow t in terms of x. If you replace t, then you will get an expression in terms or rather a function involving only an x and y, and that will be the trajectories equation. That means the equation of the path for the particle which is projected in the resistive medium. Okay, so they're applying some certain calculations here from this equation and equation 4. That means x is expression. You can easily see this one will be used actually 1 minus e to minus kt. Okay, so that's what they're using here to e to the minus kt suitably taking this one and then just you plug it in here and ultimately you can get the expression between x and y. So this is the required trajectory. Okay.